let us talk about ordinary differential equations. So, there are two things that we are going to talk about. We are going to talk about differential equations and we are going to talk about difference equations. Differential equations are things that you have already done. Difference equations, some of you might have done, most of you have probably not done the difference equations. So, we will just baseline it, we will just recap the things so that we are all talking the same language in this course. Okay. So, let us talk about the differential equation in a single variable. So, if x is a scalar, this is an example of a homogeneous linear differential equation in a single variable. Okay. Because it is a differential first order differential equation in single variable, you require one initial condition and this is the way you give initial conditions. You know how to solve this differential equation. Okay. You can take x in the denominator dx by x, that is log of x equal to at plus c, therefore, x equal to another constant c multiplied by e to the power at, at t equal to 0, x equal to x naught and therefore, it is a naught at any time t, x is x naught e to the power at. Okay. So, that is the differential equation and you know how to solve it. Okay. Now, if there is a system that is driven by an external input u, okay, then it would not be a homogeneous differential equation, but it will have the linear input component over here. How to handle this, what does this mean and so on, we will come to that in module 3, okay, that is in the third week of this course. Now, differential equations in multiple variables. Okay. Funda is the same, you have n differential equations in n variables, you can write them in the vector form. When you write them in the vector form, this is A is an n by n matrix. Okay. Why? Because A is a matrix and again I will come to the meaning of the next statement in the next week. A is a matrix that is going to map an n dimensional vector on itself, okay, and A is what we call as a linear mapping. Okay. Again, if you have heard these terms, if you have heard about linear operators or heard about this term, great. If you have not heard, absolutely no problem, that is what we are going to spend an entire week on studying. Okay. So, now if you wanted to solve this, again the way to solve it is very similar, or the result at least is very similar, and earlier we had x equal to e to the power small at multiplied by x naught, same way you will have this as well. Okay. But important thing, x naught bar multiplied by e to the power at is wrong. Why? Because x naught bar is an n cross 1 vector, e to the power at is n cross n matrix. You cannot multiply n cross 1 vector with an n cross n matrix. Okay. This is an obvious part where you will make an error, but in vector or matrix calculus, there are some blind spots where we do tend to make errors. So, those are the blind spots you need to be a little bit careful about. Let us say A is 1, 2, 3, 4, e to the power A is not equal to e to the power 1, e to the power 2, e to the power 3, e to the power 4. E to the power capital AT is what is known as a matrix exponential. Matrix exponent exists only for square matrices, not defined for non-square matrices. Okay. And we will talk about this in module 1, how to calculate e to the power at, we will talk about that in module 1. Okay. So, difference equations. Any questions about differential equations? Yeah, cool? Okay. What I am going to talk about next is incorrect. Okay. Let me say that again, what I am going to talk about next is an incorrect, it is only an approximation, I am only doing it as a motivation. So, I am taking as a teacher I am taking liberty over here, okay. But let us say you had a differential equation of this type, okay, and if you were to apply Euler's rule, okay, then dx by dt is nothing but xk plus 1 minus xk divided by tk plus 1 minus tk, or that difference we will call as delta t, okay. Right hand side it is just a multiplied by xk, okay. If we rearrange this, then you are going to get xk plus 1 equal to xk plus a delta t multiplied by xk, which is equal to 1 plus a delta t xk, okay. Let us call this as, let us say, phi bar, okay. Then x k plus 1 equal to phi bar xk. This in a nutshell I can say is a motivation for difference equations. Just the way differential equation tells you starting from x naught how x will evolve in time, likewise difference equation will tell you starting from x naught how x will evolve in discrete time, okay, that is all. This is not an actual difference equation, that is just an approximation of a difference equation. This is how we will call the actual difference equation. Again, looks exactly the same, just to distinguish between the two I have called one as an x bar phi bar, other I have not put a bar on that, okay. So how do you think xk is going to be related to x naught? Yeah, if you want you can try that out in your books. How is x1 related to x naught? Phi times or phi times x naught. How is x2 related to x naught? Phi square times, right. So x1 is phi x0, x2 is phi x1 equal to phi multiplied by phi x0 equal to phi square x0 and so on. So xk is going to be phi to the power k multiplied by x0, okay. Now another thing that you did with respect to stability, maybe I have that, okay. Let us say the continuous time representation of the system is this, the same system is represented in for a digital control in this manner, okay. So let us say, now let us talk about the stability. You have probably done this, but if dx by dt equal to ax, then it is stable if a is positive, negative, negative, right. Why? E to the power minus at decreases with time, e to the power plus at increases with time for positive values of a, right. So that is why if it is e to the power at, it is stable if a is negative, okay. Why do you see that? Because e to the power negative t, e to the power minus t or e to the power minus 2t and so on, as t becomes larger and larger, that value tends to 0, okay. When would phi to the power k tend to 0? When phi is less than 1. What if phi is minus 2? Sorry? Less than 1 in magnitude. When phi is, that is when it is stable. When phi is exactly equal to 1, it is called marginally stable, which is the same as a equal to 0, right, which means it neither decreases nor increases, so it is marginally stable, right, same fundas, okay. Question is, how are a and phi related? So let us say a is a negative value and let us say it starts with x naught, it is going to decrease like this. So this is how xt decreases. How does xk decrease? This is our x naught value, this is our x1 value, this is k equal to 2, this is our x2 value, this is our x3 value, so on and so forth. Okay. We will talk about how A and phi are related when we come to module 3. Okay. And just like before, x1 is Ax bar 0, x2 bar 1, sorry, oops, x bar 2 is A times x bar 1, which is A square x 0, and so on up to x bar k is A to the power k x bar naught. Okay, same fundus, pretty much behaves in the same manner. Okay. And again, because A is square, that is why you can do A squared, A cubed, A to the power 3 and so on. Okay. If A was, and not in this particular case, but if A is, let us say, a 2 by 3 matrix, you cannot do A multiplied by A. You can do A multiplied by A only if the number of rows and number of columns are equal, right. So, that kind of concludes. So, the main thing, main takeaway message is, if you have equation of the sort dx by dt equal to Ax, then at any time t, the evolution of x is given by this equation. Equivalently, the same system would be equivalently represented in terms of difference equation, and the difference equation would look something like this, and this is how the evolution of x in the future will look like. Okay. So, that is the equivalence, but there is a difference, and the difference is the differential equation, the solution is this entire red line. The difference equation solutions is only these points. Okay. We do not have information between these points, we have information only at this point. So, what I am showing right now is the solution of difference equation, okay, and what I am showing with curve is the solution of a differential equation, and that is the distinction between the two. Okay. For equations in single variable, we said that stability is given by A less than 0 or phi between -1 to +1. Okay. The stability for multiple variables is given by eigenvalues of A. Okay. For differential equations, lambda A should be less than 0, right. That is what some of you said in day before yesterday's class, that the poles should lie in the left half plane. Likewise, for this equation, the eigenvalues of A should lie in the left half plane. That is what this means. The two vertical lines is just the modulus, not or absolute value. No, not the absolute value, the real value, sorry, this is wrong, it is REA. Okay. In difference equation, okay, it is going to be okay. Important thing is for all lambda, even if one of the lambdas is in right half plane in the continuous case or outside the unit circle in the discrete time case, the system is unstable. So, if let us say the discrete time case, if the 3 lambdas are 0.2, 0.4 and 1.5, it is unstable. So, yeah, that brings me to the end of today's class.